Hello. In this video, we're going to talk about the high frequency model of the MOSFET, which is going to allow us to estimate the bandwidth of our amplifiers. We have talked about already the low cutoff frequency for MOSFET amplifiers, which, as we mentioned, is set by the coupling and bypass capacitors and the equivalent resistances connected to them. Typically, we will be able to select values for the coupling and bypass capacitors so that we set the low cutoff frequency to whatever value we want. Normally, we will set it low enough so that the signals in the frequency range of interest will be let through. So our low cutoff frequency will be lower than the lowest frequency of interest. In the case of the high frequency response, it's determined by load capacitances, parasitic capacitances, but also internal capacitances of the MOSFET. And we typically don't get to decide what those values are. We have to estimate them and basically live with them. The one thing we can do is if we have a particular MOSFET which does not meet the specifications, meaning it will give us too low of a high cutoff frequency or too low of a bandwidth for our amplifier, we can select a different MOSFET transistor. We're talking in discrete circuit design that may have better high frequency characteristics. But in most cases, we're just going to be estimating what the high frequency response will be. In order to do that, we can use a model of the MOSFET for high frequencies. And we can just do it by adding some capacitances, the capacitances of the MOSFET, to our hybrid pi model. So our hybrid pi model for the MOSFET consisted of the gate terminal. There was an open circuit between gate and source. And then there is a drain to source current, which is modeled via a current source, whose value is dependent on the transconductance of the transistor, but also on the voltage VGS, the voltage between the gate and the source terminals. And then sometimes, we could add an output resistance, rho. In some cases, we will just assume it to have an ideal value of infinity. But if we are modeling the channel length modulation, then we will include it in our own model. Now, in order to calculate or draw the high frequency model, we just need to add some capacitances to our model. And those capacitances are going to be a gate to source capacitance, which we're going to refer to as CPS. Names are very simple because this is the capacitance from gate to source. A capacitance from gate to drain, CPD, drain terminal, and a capacitance from drain to source. Here, drain, this is my source capacitance, C. So those three capacitances. Now those capacitances, simply come from the physical structure of the MOSFET, and we will not get into calculating the values of the capacitances based on the MOSFET parameters or anything like that in the physics. But what we will get into is how do we calculate the value of these capacitances from the capacitances that come specified in the datasheet. If you look at the datasheet for a small signal MOSFET transistor, you will notice that neither of these capacitances appear in the datasheet. What appears in the datasheet are equivalent input capacitance. So, typical datasheet pieces, say. Will be the equivalent input capacitors. It will typically appear listed in the datasheet as CSS. the equivalent output capacitance OSS, and either the forward transfer capacitance or the reverse transfer capacitance. So forward or reverse. Capacitance. See, if it is reverse, it will be RSS. If it is forward, it will be FSS. They're the same thing and they're going to have the same value. Typically, only one of them will specify. So this is different nomenclature. But how do these relate to the CVS, CVD, etc.? And it's fairly simple. The equivalent input capacitance, CISS, is going to be equal to, you'll have to look at the capacitances that can be seen from the input terminal, so to speak, the gate terminal, which are CVS and CVD. So it is simply CVS, CVD, CRSS, the transfer capacitance is just from gate to drain, and so it's very well simple, CVD. And COSS, likewise, with CVD plus CDS. Basically, the two capacitances that can be seen from the drain terminal. As you can see, this nomenclature assumes a common source configuration, one where the input is taken at the gate and the output is taken. But that's the nomenclature that it's used. Now, typically, what we want to do is go backwards, go from the values of the data sheets, be able to calculate the value of CVS, CVD, and CDS. And so we can sort of revert these equations and come up with values of CVS, CVD, and CDS in terms of CISS, CRSS, and COSS. So results will be in here. That's basically CPS equal to CISS, yes, simple equations. CPD is simply CISS, and CS to COSS minus CPD, which is with this, we should be able to calculate the three capacitances for our model from the data sheet. Now, something to note is that typically CDS is going to be sufficiently small. It's sufficiently small that can be neglected. To simplify that. But in any case, this will be the high frequency model. Again, if you wanted to eliminate CDS, you will just basically eliminate from the model and then with a simpler version of the circuit, same thing with little arrows, but this will be the more complex. There are some capacitances that I'm using here, and those will be the capacitances that go to the bulb transistor. We're typically going to be ignoring those in our calculations, but in a more complete version of the model, we will need to consider those as well. Alright, so next we're going to see how we can apply this model to estimate the high frequency response or the high power frequency